notebook and press pause. And when you're done writing it, press play again. We have a problem in that we don't have like terms, so we can't combine my two trig functions into one. I can't factor it. I have a double angle and a single angle. That's a problem. In order to be like terms, I have to have all single angles or all double angles. So what we're going to do is we're going to use the double angle identity for sine to rewrite sine of 2x. So I'm going to highlight that. So rather than sine of 2x, I wrote 2 sine of x cosine of x, which is the double angle identity for sine. And then that puts me in a really good spot because I now have something that's factorable. I have like terms. Cosine of x is my GCF. Well, not like terms. I have a greatest common factor. So I factor out cosine of x, and in parentheses, I'm left with 2 sine of x minus 1. I can then set each factor equal to 0 and solve. When cosine of x is 0, that happens at pi over 2 and 3 pi over 2. And then when I solve for sine of x, I get sine of x equals 1/2. That occurs at the angles pi over 6 and 5 pi over 6. And then, now I have all solutions between 0 and 2a. Next, write this down, press pause. When you're ready, press play again. Now, the good news is we have both cosines. The bad news is the angles don't match. So they're not like terms. I can't subtract them. There's really not a lot I can do with this. So we're going to use the same approach by using some of our identities. I'm going to use the sum identity for cosine and the difference identity for cosine. And let's see, cosine of pi over 4, again, cosine of x plus pi over 4, I use the sum identity. That's right there. Cosine of x times cosine of pi over 4 minus sine of x, sine of pi over 4. And then over here, I'm going to use the difference identity for cosine. And notice this is all in parentheses. I'm going to subtract the quantity. That becomes cosine of x times cosine of pi over 4 plus sine of x times sine of pi over 4. That whole thing is equal to 1. Now, what I noticed is I have a cosine of x times cosine of pi over 4 over here, and I have the same thing over here, and it's going to be subtracted. So these are going to cancel out, and this negative sign gets distributed over here. So I end up with minus 2 sine of x sine of pi over 4. And again, that's still equal to 1. And sine of pi over 4 is square root of 2 over 2. And then my 2's cancel. And I'm left with negative the square root of 2 sine of x equals 1. Divide both sides by negative square root of 2. And then I rationalize. So sine of x is equal to negative square root of 2 over 2. And my reference angle is on my unit circle. It's one of my standard angles. It's pi over 4. So sine of x is negative. So that means I am in quadrants 3 and 4. Both with reference angles of pi over 4. So I end up having x equal 5 pi over 4, that's here, that's 1, it's pi plus the pi over 4, and 7 pi over 4, which is 2 pi minus the pi over 4, both with the same reference angle, quadrants 3 and 4. Now, I'd like to give you a chance to try to solve one of these using an identity. And I want you to solve it in degrees between 0 and 360. Press pause on your video and then again press play for the answers. And here we go. We rewrite cosine of 2 theta as 1 minus 2 sine squared theta. You could have also used 2 cosine squared theta minus 1. You should have gotten the same answers. I would have used one of those identities rather than the cosine squared minus sine squared identity, because I would have ended up in a situation where I would have had to use another identity or something because it wouldn't have been factorable, and I need just one trig function to solve for. So in this case, I subtracted 1 and divided by negative 1, and I got 2 sine squared x, 2 sine squared theta equals 1 minus square root of 3 over 2. Then I divided both sides by 2, and then I took the square root. Remember, it's really, really, really important that you remember it's plus or minus when you take the square root. And then in my calculator, I figured out the reference angle was 15 degrees. And I knew that sine was plus or minus, so I had an answer in every single quadrant. So my answers would be 15 degrees, that's the first quadrant, 165 degrees, that's 180 minus 15, that's the second quadrant, 195, 180 plus 15, that's the third quadrant, and 345, that's 360 minus 15 in the fourth quadrant. Now, there is another way to solve this kind of problem. I don't know if you noticed, but cosine is equal to square root of 3 over 2 on one of our standard angles in the unit circle. So another approach would be to find that reference angle, and again, that's 30 degrees. And since cosine is positive, it's going to be in the first quadrant and in the fourth quadrant. Now, theta is between 0 and 360, but 2 theta is between 0 and 720. So while I have these two answers that fit very nicely between 0 and 360, I also need to find coterminal angles all the way up to 720 degrees. And I do that by adding 360 to each of the standard angles or each of my solutions in the within the constraint 0 to 360. I add 360 to each of these. Now I have all the answers where 2 theta would equal square root of 3 over 2. And at that point, I'm able to solve each of these for theta by dividing them by 2. And you'll notice that all my angles are exactly what I got on the previous page. 15 degrees, 165, 195, and 345. Pretty nice. There's no perfect approach, and the correct way to do a problem is the way you see it first, but I will tell you that it tends to be easier to solve it this way. And sometimes it's not possible to solve it using an identity, and you have to use that approach where you adjust your constraint and you find all your solutions for your double, triple, or quadruple angle, and then solve for theta separately. Now, I want you guys to give this one a try. There is no choice with this one but to solve it using the method that I had just discussed. And when you're ready, press play again, but pause right now. And we're going to only find solutions between 0 and 2 pi. Press pause and again resume when you're ready for the answer. Here we go. I recognized that the reference angle was going to be pi over 4. I adjusted my constraint. I had 0 to 2 pi for x, but 3x is between 0 and 6 pi, multiplying each of those by 3, of course. So on my unit circle, 3x is going to be between at pi. 3x is going to equal pi over 4, or it's going to equal 3 pi over 4. I then took each of those and I added 2 pi to it, and I got 9 pi over 4 and 11 pi over 4. Again, I'm adding 2 pi, which is 8 pi over 4. Then I noticed that I did not nearly hit that constraint. I'm going to add again another 2 pi to each, 17 pi over 4 and 19 pi over 4. And then at that point, if I were to add 2 pi to each of these again, I would be higher than the 6 pi. Then I took each of these and I divided by 3. So now I have 6 answers: pi over 12, pi over 4, 3 pi over 4, 11 pi over 12, 17 pi over 12, and 19 pi over 12. Now, if I'm instead looking for all solutions, it's actually easier when you have one of these triple angles to do all solutions. So looking back, I had tangent of 3x equals 1. I recognized that my reference angle was going to be pi over 4. Between 0 and 2 pi, that gives me pi over 4 plus pi over 4 and 5 pi over 4. Now, I want to write out the equation for all solutions. So for each of these, I could say 3x equals pi over 4 plus 2k pi, and 3x equals 5 pi over 4 plus 2k pi. But I notice that these two answers are exactly pi apart. Let's see. They're exactly pi apart. So every time I add another pi or subtract another pi, I'm going to get the same answers. So I decided to write one equation, which is 3x plus pi over 4 plus k pi, and that would represent all the solutions. Notice that the increment here is the period of tangent, and that makes sense. And then what we do is we solve for x by dividing pi over 4 by 3 and k pi by 3. So clearly there's an error here. It's not pi over 4. It is pi over 12. Let's see if I can write with my mouse. Switch one up. This should be a 12. Divide the pi over 4 by 3. Divide the k pi over 4. K pi by 3 as well. And now these are my solutions. And again, k is an integer. Next, we are going to solve this quadratic equation. This isn't much different than what you did yesterday, except I have a triple angle in there. And again, we're finding all solutions. So we first factor, and then we set each of the factors equal to 0 and solve. So I know that my reference angle is going to be, what is my reference angle going to be? Pi over 6. And I really should have this here. Let's change this a little bit. It's 1/2. Okay, so my reference angle is pi over 6, and this is going to be in quadrants 3 and 4 because sine is negative, and that gives me 7 pi over 6 and also 11 pi over 6, and that is right here. Okay. I also have to think about the fact that sine of 3 theta is 1. So sine of 3 theta is 1. That occurs at pi over 2. So I can write 3 theta equals pi over 2 plus 2k pi. And then to each of these, I write plus 2k pi because, again, you're going to find answers on your unit circle in the third quadrant, the fourth quadrant, and then also at pi over 2. So once I have these written, let's see, we'll highlight them. This guy, and this guy. I'm going to solve each of them for theta. Oops, hold on. I highlighted the wrong thing. Here we go. Here's the one. I took each of those answers and I added 2k pi to them, and then I divided by 3. I divided pi over 2 by 3 and also 2k pi over 3. There is my first part of my answer. Then this one did the same thing as well, divided the whole thing through by 3, divided this whole thing through by 3, and now I have a 3-part answer. This guy, and this guy. Those are my solutions. Now, write this down, press pause when you are ready to move on. Now, we have a problem. There is no identity that I know that would allow me to write sine in terms of cosine. Remember, sine squared theta equals 1 minus cosine squared theta, but neither of these are squared. And there's really only one way to do this without the calculator, and that is to square both sides of your equation. So what I did was I squared the left side and I squared the right side. When that happens, I got sine squared x minus 2 sine x cosine x plus cosine squared x is 1. Now that's nice because sine squared x plus cosine squared x is 1. And then I still have the minus 2 sine x cosine of x, again, still equal to 1. And then I subtract 1 from both sides and divide both sides. I didn't divide anything. I recognize sine of x cosine of x is sine 2x. Divided both sides by negative 1, and now I know sine of 2x equals 0. That is going to happen when the terminal side of my angle is on the x-axis. So that happens at 0, and it also happens at 180. Now, I have to adjust my constraint so that now, rather than x being between 0 and 360, I have 2x being between 0 and 720. So to each of these, I had to add 360 degrees. So I added 360 to get 2x equals 360, and I added 360 here to get 2x equals 540. If I were going to add the 360 again to each of these, I would be outside of this constraint, so I stop there. Then I solve for x by dividing each of those by 2. So I get x equals 0, x equals 90, x equals 180, and x equals 720. But one thing you have to remember is that when you square both sides of an equation, you need to check for extraneous solutions. And you do that by substituting into the initial equation. And if you put 0 in here, you'd have sine of 0 minus cosine of 0. Well, sine of 0 is 0. Cosine of 0 is 1. You'd get 0 minus 1 would be minus 1, and that's clearly not 1. If you plug in 90, it will work. If you plug in 180, it will work. If you plug in 270, it will not. Sine of 270 is negative 1. Cosine of 270 is 0, so you'd get negative 1 equals 1, which is clearly not true. So I get two solutions, 90 degrees and 180 degrees. Now check my website for your homework assignment. Have a nice day.